Welcome to this presentation on maths for heating engineers. This was first presented to eco-technicians a couple of years ago and has since been updated. The object is not to turn you all into Carol Vorderman, but to try and show that maths isn't as scary as you think it is, and there are often simple ways of doing complex sums. So let's start off with units of measurement. Most of these we know, such as length, can be measured in meters, millimeters, kilometers, time in seconds, minutes, hours, etc., etc. You can call a unit of measurement anything you like. You can measure length in daves or threads if you like, but if nobody else knows what those measurements mean, then they're not a lot of use, so we tend to stick to the ones we all know. Some simple formula. Some of these you will know. Speed equals distance over time, measured in kilometers per hour, meters per second, miles per hour, etc. Area of a rectangle, length times the width, useful for doing floor areas, for working out heat loss calculations, etc. Area of a triangle is half the base times the height. Area of a circle, pi r squared. Pi is a constant, 3.14 in round terms. The circumference of a circle is 2 pi r, or pi times the diameter. This can be useful for working out how much pipe we have left on a coil. For example, if we had a coil of underfloor heating pipe with a diameter of 1 meter and we had 10 turns on the coil, we could work out the length without opening it all up. So from our formula, pi times the diameter times 10 gives us 31.4. So we'd have 31.4 meters. Obviously you could round this to 3 instead of pi, which gives you roughly 30 meters, which is near enough when you're measuring out. Volume of a cuboid, i.e. a room, is the length times the width times the height in meters cubed. Again, useful for heat loss calculations. Volume of a sphere, it's one you probably won't use that often. Volume of a cylinder, which is all a pipe is at the end of the day, is pi times the radius squared times the length. So if you know your internal diameter of your pipe, the radius is half of that, so pi times the radius squared times the length of the pipe will tell you how much water you've got in the pipe in meters cubed. Mass flow rate. This is one we use in heating calculations. Kilowatts equals dT, which is temperature differential, times the SHC, which is specific heat capacity of the fluid, times the speed in litres per second. So when we're working with formulae, the one thing we do have to remember is that both sides of the formula are always in balance. So what goes on the left hand side must also go on the right hand side. Whatever we do to the left, we have to do to the right. So if we try to work out the value of x in this formula here, 3x equals 4 plus x, to keep the equation in balance, we can remove x from each side, and we'll see that 2x equals 4, because we need all the x's on one side. We can't work out the answer if we've got x's on both sides. So by subtracting x from both sides, we get 2x equals 4. Now we need to get down to 1x. So if we divide both sides by 2, 2x divided by x is, 2x divided by 2 is x, and 4 divided by 2 is 2. So x equals 2. Another thing to remember, multiplying by 1 over x is the same as dividing by x. So 6 times 1/3 is the same as 6 divided by 3. A third of 6 equals 2. 6 divided by 3 equals 2. When multiplying or adding, the order is not important. 3 times 4 is the same as 4 times 3, and 5 plus 6 is the same as 6 plus 5. Another useful thing is that fractions can often cancel out. So, for example, we're multiplying 1/3 by 3/5. The 3 on the bottom of the left-hand side cancels out the 3 on the top of the right-hand side. So 1/3 times 3/5 equals 1/5. Anyone can do algebra. It's nothing to be scared of. And in algebra, we use letters to substitute for known or unknown values. So if we take our speed equation, velocity, which is speed, equals distance over time. So v equals s over t. So if we want to find out how long it will take us to travel 30 kilometers at 15 kilometers an hour, we transpose the equation to t equals s over v. T equals 30 divided by 15, therefore t equals 2 hours. So at 15 kilometers an hour for 2 hours, we'd travel 30 kilometers. A useful aid when working with simple linear equations is the magic triangle. And what the magic triangle says, that A equals B times C, therefore B equals A over C, and C equals A over B. To find A, we cover it up if we know B and C, so A equals B times C. And then if we want to find B, we cover up B, and that tells us that B equals A over C. And in the same way, to find out C, we cover it up, and that tells us that A over B equals C. One of the main uses for the magic triangle, which we probably all remember from school, is Ohm's law. And Ohm's law states that the current flowing through a resistance is proportional to the voltage applied across that resistance. V equals IR. V is measured in volts, I current is measured in amps, and R resistance is measured in ohms. As we said, Ohm's law, the current flowing through a resistance is proportional to the voltage drop across the resistance. So if we have a voltage of 230 and a resistance of 115 ohms, what's the current? Well, we cover up I, and we know that current equals V over R. So if the voltage is 230, the resistance is 115, I equals V over R equals 230 over 115 equals 2, and that's measured in amps. So if we have 500 milliamps flowing through a resistance of 24 ohms, what's the voltage drop across the resistance? Well, V equals IR. 500 milliamps is 0.5 amps times the voltage 24 gives us 12 volts. So 12 volts applied across resistance 24 ohms would give us a current of half an amp. We can also use the triangle for electrical power. The power in watts equals the voltage in volts times the current in amps. So if we wanted to know how much current does the 3 kilowatt kettle draw, well, we know from our triangle that I, the current, equals the power over the voltage. So if we take 240 volts, which used to be the UK standard, I equals P over V equals 3000 divided by 240, which equals 12.5 amps. So our 3 kilowatt kettle would draw to 12.5 amps at 240 volts. This is about the maximum you can draw from a normal 13 amp plug. So if we want to work out what the resistance of the element was, we can use the two triangles. So we can work out the current because we know the power and we know the voltage. So the current is 3000 divided by 240 equals 12.5 amps. If we go to our other triangle to work out the resistance, V over I, so it's 240 divided by 12.5, which makes our resistance 19.2 ohms. So if we now put that same kettle onto a 230 volt supply, which is what we tend to get these days, we know that I equals V over R, which equals 230 over 19.2, which gives us 11.98 amps. So now we can work out the power. Power is V times I equals 230 times 11.98 equals 2,755 watts, 2.7 kilowatts. There is a mistake on this page. That should read P equals VI, not P plus VI. Shortcuts and guesstimation. Who knows their 19.5 times table? Not many people. But we don't need to know our 19.5 times table to multiply by 19.5. 5 times 19.5 is exactly the same as 5 times 20 minus 5 times a half, half being the difference between 20 and 9.5. So 5 times 20 is 100, 5 times 0.5 is 2.5, 100 minus 2.5 is 97.5. Fairly simple. Another place where we can use guesstimation is to work out a rough answer to a sum, so that when we use our calculator we know whether we're in the right ballpark. So if we're trying to work out the area of a rectangle 4.2 meters by 6.3 meters, we know area equals length times width. So if we just take the integers, which is the whole parts of the numbers, we know that our area has got to be bigger than 4 times 6, so 24 is the absolute lower limit we should expect. If we went up, rounded our integers up to 5 and 7, then the upper limit would become 5 times 7. So we now know our answer should be somewhere between 24 and 35. And we can refine this slightly more by setting an upper limit as 5.5 times 6.5, which would be 29.25. So now we know our answer should be between 24 and 29.25. So we punch the numbers into our calculator and we get an answer of 26.46. That's in our ballpark, so we know we're right. If our answer had come out at 264.6, we would know we'd made a mistake because it's nowhere near our ballpark. And we can break down a complex sum like 4.2 times 6.3 into smaller bits, i.e. 4 times 6 plus 4 times 0.3 plus 0.2 times 6 plus 0.2 times 0.3, which is 24 plus 1.2 plus 1.2 plus 0.06, which gives us 26.46. So even if we didn't have a calculator, we could quite easily work out the sum. Now we come on to mass flow rate, sometimes known as volumetric flow rate. And this equation tells us that the power in kilowatts is equal to the delta T, or temperature differential, times the specific heat capacity times the speed of flow in litres per second. We know that the specific heat capacity, or SHC, of water is approximately 4.2 kilojoules per kilogram degrees centigrade. In other words, it takes 4,200 joules of energy to raise 1 kilogram, or 1 litre, of water 1 degree centigrade, or 1 degrees Kelvin. The units centigrade and Kelvin are identical units, but the scales start in different places. Kelvin starts at absolute zero, which is around about minus 273 degrees centigrade, and centigrade scale starts at the freezing point of water, 0 degrees C. So if we wanted to work out the flow rate for a condensing boiler with a DT of 20, so the delta T times the specific heat capacity is 84. It's 4.2 times 20. So a boiler of 42 kilowatts output would need a flow rate of 42 divided by 8.4, which is 0.5 litres per second. So if we halve the flow rate to 0.25 litres per second, what would our delta T be then? Well, our kilowatts is still the same, 42. And if we put the figures into the triangle, we can see that the delta T, 4.2 times the delta T, equals 42 divided by 0.25. That's our kilowatts divided by our flow rate. So therefore the delta T is going to be 168 divided by 4.2, which is 40 degrees centigrade. In practice, our modern condensing boilers wouldn't like that higher DT and would modulate down their output. So if we wanted to get back to a delta T of 20, the boiler would have to halve the output